Hi everyone, my name is Abhishek and I'm going to present our work, MIMO-Zak-OTFS in doubly selective channels, IO relation estimation and detection. This work was jointly done with my PhD supervisor, Professor Chokalingam at Indian Institute of Science, Bangalore. This is the overview of the presentation. So I'll start with the introduction. In the next generation of wireless communication systems, high frequency band and high mobility scenarios are going to be expected, and that will result in doubly selective channels. OTFS modulation has been shown to be robust in those doubly selective channels. In OTFS, information symbols are multiplexed in delay Doppler domain. Receiver tasks such as symbol detection and channel estimation are carried out in delay Doppler domain. Conversion from delay Doppler domain to time domain uh, is carried out via inverse Zak transform at the transmitter in Zak-OTFS. Also in Zak-OTFS, DD domain pulse shaping filters are used to limit time duration and bandwidth of the transmitted signal. Choice of these filters play a vital role in the effectiveness of estimation and detection schemes, as we will see. In this work, we are concerned with MIMO-Zak-OTFS, which is Zak-OTFS in MIMO setting, where multiple transmitter antenna and multiple receiver antenna are used. So I'm going to present the MIMO-Zak-OTFS system model, but let's first see Zak-OTFS system model. This is the block diagram of Zak-OTFS system. In Zak-OTFS, basic information carrier is quasi-periodic DD domain pulse, as shown in the left corner of this slide. And it is localized in the delay Doppler domain in the fundamental region. We limit the time duration and bandwidth of this quasi-periodic DD domain pulse by using DD domain pulse shaping filter. And action of those filter is given by a twisted convolution. Then we convert the DD domain signal into time domain signal via inverse Zak transform. The time domain signal then interacts with the channel, and at the receiver, we convert the time domain signal back to delay Doppler signal, and then we pass it through receive pulse shaping filter, whose action is also given by twisted convolution. And then we sample it and get the information symbols at the receiver side and use them to estimate the IO relation and detect the symbols. So these are some equations that depict the signal flow in Zak-OTFS. At the transmitter, the fundamental region is divided into Mn bins. Each bin contains an information symbol that is denoted by xkl. K ranges from 0 to m-1, L ranges from 0 to n-1. And these information symbols are embedded in delay Doppler domain by this equation, second equation. This ensures the quasi-periodicity of discrete DD domain pulse. And then we lift this discrete domain pulse to continuous domain by modulating with the direct delta function. This continuous DD signal is then passed through transmit DD domain filter, and that action is given by a twisted convolution. So we receive xdd wtx tau nu is equal to wtx tau nu twist convolve with xdd tau nu. This pulse shaped DD domain signal is then converted to time domain by inverse Zak transform. Then this time domain signal interacts with the physical channel h physical tau nu, which is given by summation of hi delta tau minus tau nu delta nu minus nu I, where I ranges from 1 to p. P is the number of paths, hi is the fading coefficient associated with the ith path, tau I is the delay, and nu I is the Doppler. At the receiver, this time domain signal, we receive the time domain signal and then we convert that to delay Doppler signal by Zak transform. This DD domain signal is then passed through receiver filter, which is matched with the transmit filter, and that is given by the output of that is given by YDD WRX tau nu is equal to WRX tau nu twist convolve with YDD tau nu, and then we can finally obtain this end-to-end IO relation in continuous domain. So YTD WRX tau nu is then given by WRX tau nu twist convolve with H physical tau nu twist convolve with the WTX tau nu twist convolve with XDD tau nu, which can be written as YTD WRX tau nu is equal to H effective tau nu twist convolve with XDD tau nu plus WRX tau nu twist convolve with NDD tau nu. This H effective tau nu is we denote this as effective channel. After this, the YDD WRX tau nu is then sampled on information grid to give the discrete DD domain received symbols YDDKL, which is given by YDDKL is equal to YDD WRX at tau is equal to K tau P by M and nu is equal to L nu P by N. And similarly, H effective tau nu and NDD tau nu are also sampled on information grid. The end-to-end relation, IO relation in discrete domain is then can be obtained as follows, which relates the YDDKL and XDDKL. This relation is then vectorized can be vectorized, and we can obtain y is equal to h effective x plus n, where h effective is the mn cross mn effective channel matrix. This effective channel matrix can be obtained from h effective KL using the equation 1. So we obtain the y is equal to h effective x plus n relation for CISO-Zak-OTFS. Now let's do with the MIMO-Zak-OTFS system. So this is the block diagram of MIMO-Zak-OTFS system model, and there are NT transmit antennas, and NR receiver antennas, and the physical channel uh, between any two transmitter and receiver is denoted by HQP tau nu, where Q is the receiver antenna, and P denotes the pth transmitter antenna. Effective channel between pth transmitter antenna and qth receiver antenna is given by WRX tau nu twist convolve with HQP tau nu twist convolve with WTX tau nu. We can obtain received digidomain signal in discrete domain at qth receiver antenna by summing up all the transmitted symbols from all the transmit antennas. Then we can vectorize this equation, and we can obtain yq is equal to summation p is equal to 1 to nt HQP XP plus NQ. HQP is the effective channel matrix between qth receiver antenna and pth transmitter antenna. We can combine all these equations, and we can obtain y MIMO is equal to h effective MIMO x MIMO plus n MIMO, which gives the compact relation between all the transmitted symbols and all the received symbols. And by IO relation estimation, we mean that we want to estimate this h effective MIMO matrix. So I'll now present the IO relation estimation scheme. We use exclusive pilot frame for IO relation estimation. We consider 2 cross 2 MIMO-Zak-OTFS. We have two transmitter antennas and two receiver antennas. At transmitter 1, the impulse pilot is located at the origin in the fundamental region of DD domain. At transmitter 2, the impulse pilot is located in the middle of the fundamental region of DD domain. These two pilots interact with the effective channel H effective 11 and H effective 12, and we get the received pilot frame as shown in the figure. We can use this received pilot frame uh, at the receiver 1 to actually estimate H effective 11 and H effective 12. So to do that, we divide this received pilot frame into two regions, that is the red shaded region and the green shaded region, and we use these regions to estimate H effective 11 and H effective 12. From the red region, we pick the symbols which will be helpful in estimating H effective 12, and from green region we pick out the received symbol which will be effective for estimating H effective 11. So we use these equations to actually obtain the estimate of H effective 11 from the received pilot symbols. What makes it work is that the impulse pilot, when it interacts with the H effective channel via twisted convolution, what that means is that the H effective channel will be translated to that impulse location with some phase term, and we can easily get that information of H effective from the received pilot symbols. Once we have H effective 11 and H effective 12, we can similarly use the received pilot frame at the receiver 2, and we can get H effective 21 and H effective 22. And by using H effective 11, H effective 12, H effective 22, and H effective 21, we can actually construct the effective channel matrix H11, H12, H21, and H22 using the equation 1 that was in the previous slides. We can then stack them up and actually obtain the H effective MIMO for this 2 cross 2 MIMO-Zak-OTFS. This is the estimated IO relation that we will use for signal detection. So once we obtain the estimated effective channel matrix, H effective MIMO, we can use that to detect the signal in DD domain. For that, first we use MMSE equalizer. After that, we improve upon MMSE solution by using MMSE less. In MMSE less, we start with initial solution vector as MMSE solution, and then we look in its one symbol away neighborhood. One symbol away neighborhood is correction of all the vectors which differ from MMSE solution in one coordinate. We search this neighborhood for best solution vector. Best solution vector in the sense that it gives lower ML cost. And once we found that vector, we assign that to be current solution vector, and then we iterate this whole process again and again till we reach the local minima, and that solution is declared as MMSE less solution. I'll now present the results and discussion. So we use the simulation parameters as follows. We use a 2 cross 2 MIMO-Zak-OTFS system. We have a frame size of 12 cross 14, that is m is equal to 12 and n is equal to 14. Doppler period is 15 kilohertz. Bandwidth is 180 kilohertz, and maximum Doppler is 815 hertz. Maximum delay is 2.51 microsecond, and number of paths are considered to be 6. We use vacuolar channel model, which has fractional delay Doppler, and we use three filters, three pulse shaping filters: sync, Gaussian, and Gaussian sync. And we compare the estimation schemes for these filters in MIMO in 2 cross 2 MIMO-Zak-OTFS. This is the MSE performance of the proposed IO relation estimation scheme for different filters in 2 cross 2 MIMO-Zak-OTFS. MSE is described as given in the slide. It is the Frobenius norm of H effective MIMO minus H effective het MIMO square divided by Frobenius norm of H effective MIMO square. Here we can see that the Gaussian filter gives the best MSE performance. This is due to the fact that Gaussian filter is very localized and it has very low side lobes. So we can estimate the H effective taps from received pilot frame very effectively. This is the BR performance under perfect CSI. Here we assume that we know H effective MIMO, and under this scenario, we compare the performance of sync filter, Gaussian filter, and Gaussian sync filter, and we use two detection algorithms, MMSE and MMSE less. Here it can be seen that sync filter and Gaussian sync filter perform way better than Gaussian filter. This is because sync and Gaussian sync filter has null set information grid sampling point that results in very less intersymbol interference, and that is the reason its detection performance is better. But in Gaussian filter, its main lobe is large and there's high non-zero value at the sampling points. It results in intersymbol interference, and the detection performance is not that good. It can also be seen that the MMSE less shows a good improvement over MMSE. There's a 6 dB gain at 10 to achieve the 10 raised per minus 3 BER for sync and Gaussian sync filter. This is the BR performance with IO relation estimation. Here we don't assume that we have the H effective MIMO, but we estimate it using our proposed IO relation estimation scheme. And then we compare the performance of three different filters, sync, Gaussian, and Gaussian sync. And we use two algorithms, MMSE and MMSE less. Here it can be seen that Gaussian sync filter gives the best performance among the three. That is because it has the good estimation performance as well as good detection performance. Sync filter has good detection performance, but due to its very high side lobes, its estimation performance is very less. With Gaussian, it has the good estimation performance because of its localized nature, but its detection performance is way worse because of intersymbol interference. And that gives an edge to Gaussian sync filter, which has both the advantage of good estimation and good detection. That's why its performance is better. And MMSE less shows improvement over MMSE for all the three filters, but for sync filter and for Gaussian sync filter, this improvement is uh, very good. This is the BR performance with IO relation estimation for 8QAM. So earlier the experiments were for BPSK modulation. This is for 8QAM modulation. Here it is very clear that Gaussian sync filter performs way more better than the Gaussian filter and sync filter, and that is due to its good estimation and good detection performance. Some conclusions. We investigated the problem of IO relation estimation and signal detection in MIMO-Zak-OTFS. We proposed IO relation estimation scheme using exclusive pilot frame. We improved upon MMSE detection performance using MMSE less. Gaussian filter achieved very good MSE performance using proposed estimation scheme. Gaussian sync filter achieved good BR performance using proposed estimation and detection schemes. Thank you.